Alright, so for question 5, you are given an array of numbers and we want to know whether this particular array could be the post-ordered traversal of some binary search tree. In other words, the idea is that is it possible to construct a binary search tree that contains all the following numbers such that if you do post-order on this binary search tree, you're going to get exactly this array. Now, first let's make clear, right? Why is it not possible for any post-order traversal to be coming from a binary search tree? Right, so let's say we only have 3 numbers. Let's say 1, 2, 3. Let's try to see what are all the different trees that we can get out of just 3 numbers. Alright, so let's say if I have 3 numbers, I can insert them into the binary search tree in any particular sequence, right? And there are different sequences I can do that. So one way is that, okay, so let's say it's 1, 2, 3. So that's one possible sequence. Another sequence is 1, 3, 2. Another sequence is 2, 1, 3. Another one is 2, 3, 1, or 3, 1, 2, or 3, 2, 1. So these are all the different permutations that we can get out of 3 numbers, right? And if I want to construct all possible binary search trees, I can generate all the permutations and see what kind of binary search tree I get. So if I insert it in the following way, so then 1 will be the root, and then I have 2, and then 3. So that's the 3 that I get. If it is 1, 3, 2, what does it look like? So it's going to be 1 as a root. I have 3 as the right child of 1. Then I have 2 on the left child of 3, right? If it is 2, 1, 3, then I have 2 as a root. 1 will be on the left, and 3 will be on the right. If it is 2, 3, 1, then 2 will still be the root, 3 will be on the right, 1 will be on the left. Now if it is 3, 1, 2, so it will be 3 here, 1 here, and 2 here. If it is 3, 2, 1, then it's 3, 2, 1. Right, so these are all the different trees I can construct from just 3 numbers. Is there any other possible 3? No, right? Because there are only 3 factorial possible permutations of 3 numbers. So this is all the different ways I can construct the trees. Now, which means that let's actually now try to do post-order traversal from each one of them. So what is the post-order here? If it is 1, 2, 3, what is the post-order traversal of this tree? So it will be 3 to 1. Because post-order means that we go from the child, right? So parents say go to my child, so it's going to be 3 to 1. So how about this one? So this one will be 2, 3, 1. So that's my post-order traversal. So here it will be 1, 3, 2. Right? Here it will be 1, 3, 2 as well. This is going to be 2, 1, 3. This is going to be 1, 2, 3. So these are all the post-order traversal, right? That you can get out of these binary search trees. Now, which means that some of the arrays that I can make up with 3 numbers may not be a possible binary search tree post-order traversal. So let's say if I have an array which is 3, 1, 2. Can I get this array out of a post-order traversal of any binary search tree? So earlier we have generated all the possible binary search trees containing 3 numbers. We have gotten all the possible post-order traversals. And this particular number has never appeared, right? Which means that I cannot construct a binary search tree that contains these 3 numbers and yet still get a post-order traversal that is going to get me this particular array. This one is not possible. Alright, so for now I just want to emphasize that there are going to be some sequences that cannot be a post-order traversal of a binary search tree. Then we will then talk about how to identify it. Alright, so is everybody okay, right? Okay, so now we know that this is not. I mean, we can see that there is no one that is actually like that, right? So which means that you already have an algorithm. And one algorithm that you can do is to generate all the permutations, construct all the binary search trees, and check the post-order traversal of every one. So that's one valid algorithm. If we were to do that, what would be the complexity? So first of all, I have n numbers. I'm going to generate all the possible permutations. What is that number? N factorial. And then I'm going to construct the binary search tree. And earlier, we did this earlier, right? We construct the binary search tree from scratch. So, and we realized that the most number of times that we can do it is going to be n times n minus 1 divided by 2, right? So this is basically coming from question 4 earlier. If you're going to construct a linear tree, in the worst case, we're going to get n times n minus 1 divided by 2. And finally, we need to get the post-order traversal. So the post-order traversal will be the same as in order. So there's going to be O(n). So it's going to be very complicated, right? We need to do essentially n factorial. And for every n factorial permutations, I need to construct the binary search tree and then do post-order traversal to check. So then the whole complexity is going to be n factorial times n squared for this algorithm. Right? This is an algorithm that essentially generates all the possible permutations, construct every binary search tree, and then check the post order and check whether or not it's the same as the array that we have or not. So, which is why I always mention, right? So there is always the simplest algorithm which generates all possible cases. So you can always think of one. It's just that sometimes it's too complicated, I mean in terms of the computation, that we can't actually execute this. But this is a valid algorithm. It means if you generate all the possible binary search trees, we can check whether it's possible or not. Alright? Now, I'm going to go on to the second possible algorithm to try to identify whether an array is a post-order traversal of a binary search tree. And actually, if you think about this, it actually comes from the property of the binary search tree itself. So let's first start with a binary search tree. Okay, so I need an example of a binary search tree. Let's say, for example, that this is the binary search tree that we are trying to do, right? Now let's talk about what is going to be the post-order traversal of this tree. Can someone give me that post-order traversal? What is that post-order traversal? So 5, 7, 6, 9, 11, 10, 8. Okay, so that is the post-order traversal, right? And we can actually see that there is some structure to this array. So what is that structure? So firstly, what is the last number? The last number will always be, for post order, what is going to be the last number? The last number will always be the root. So which means that you're going to have a structure where you're going to have a root. Now, what is this part? So you have 9, 11, 10. that part essentially is, where does it come from? It comes from the right subtree, right? And how about this part? This part is coming from the left subtree. So that's the structure, right? So what is a binary search tree? A binary search tree is a tree where everything on the left is going to be smaller than the root, and everything on the right is going to be larger than the root. Which means that given an array, if we take out the last element as the root, we should be able to divide the array into two pieces, such that the left piece is all going to be smaller than the root, and the right piece is going to be all larger than the root. So that we can do this recursively. So in this case, we have an array that essentially already fulfill that condition, right? So here we can take this as essentially another subtree, which is here. And because the post order is recursive, so then we can go back and check this itself should be able to be divided into a root, and then I should be able to divide this into two halves, where the left part is going to be smaller than the root, and the right part is going to be larger than the root. So we just need to do this recursively, and if everything holds true, it's going to be the post order of a binary search tree. Now I'll give an example of something that cannot be a post order traversal. So for example, let's take a look at this array, or for the same tree, alright? Or for some binary search tree containing the same number. Now, so this particular array cannot be a post order. So why? Alright, so let's see. Now, so we have this as a root, because this is the last number. And given the last number, we need to be able to divide this into two. So then we're going to be looking for numbers that are actually smaller than 8, and numbers that are larger than 8. So then if we go down to the left, we realize it is larger than 8, this is smaller than 8, and this is what we think will be the dividing point. Because 8 is going to divide the array into two. The part that is larger than 8, and the part that is smaller than 8. But clearly here, you see that not all the numbers are actually smaller than 8, which means that this violates the binary search tree requirement. So now how do we do this? Essentially we just do this recursively. We take an array, right? So let's take a look at the actual array that they are describing, that is in the question. So, alright, so this is 5, 7, 6, 9, 11. Okay, that's actually the same array, right? Yeah. But in this case, then this is a root. So I know that this is a root, and I know that I can go to the left, larger, 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 and this is the dividing point. So then I know that on my right, I have 9, 11, and 10, and on my left, I have 5, 7, and 6. So at this level, this holds true. Then I just need to do this recursively. I just go down. Now I need to check whether this itself is a binary search tree. So then 10 is a root. And then I go to the left. This is the dividing point because this is larger, this is smaller. So 11 here, 9 is here. And here, this is a root. And this is the dividing point. So 7 here, 5 is here. Then essentially we already have the condition that it's a binary search tree. So we just do this recursively, and we will find out whether or not it's a post order of a binary search tree. Alright? So that is the case for the second algorithm. So there is a third algorithm, which is actually also the simplest one. So for the third algorithm, we are going to consider this again, right? And we know that we can get this in the post order traversal. So in the post order traversal, So we have 5, 7, 6, 9, 11, 10, and 8. So we know that the last number that we are going to visit is going to be the one that is at the root. And generally speaking, in a binary search tree, every time you add a new number, it's going to go lower, right? So in the insertions, so for inserting nodes into the binary search tree, the later you count, the lower you go. But when we do post order, when we read it, the higher you are, the later you count, which means that the order insertion and the post order are actually opposite to one another. So to check whether or not something is a post order traversal of a binary search tree, all we need to do is just to take these numbers and then construct a binary search tree. But we're going to take it in the opposite order. So then we're going to do this, right? So for example, let's see what kind of tree we're going to get. So we're going to start with 8. So then 8 is a root. Then we insert 10. So we go to the right. We insert 11. 11 is on the right of 10. We insert 9. 9 is going to be on the left of 10. 6. So 6 is here. 7. 7 is here. 5. 5 is here. Then we just need to read this out again. And the post order, we just need to compare that they are actually the same. Then that's going to give us the post order traversal.
So what's the relationship between insert and post order?
So insertions, when you insert, right, the later you insert, the lower you go. So for example, in this case, I'm inserting 5, the last one. So it goes to the lowest possible level. But in the case of post order, the ones that is the lowest is actually the one that is going to be read first. So the post order traversal and the order insertion are actually opposite to one another. So one favors the first one that gets inserted, the other one favors the last one that actually gets inserted. Alright, so this is going to be the third algorithm. Alright, so I'm going to summarize this. 3 things. So one possible algorithm is that we generate all permutations. Create BST for each one. And then do post order and check against the array. Alright, so that's one algorithm we can do. Just generate all the possible binary search trees and then check one by one. The second possibility is that we are going to do this recursively. Okay, so we are going to ensure that when we take the last element as root, we are going to divide the array into 2, into left side and the right side. And the left side is all smaller than the root, and the right side is all larger than the root. And we can do this recursively, and if we can do that, then it's a binary search tree. And the third algorithm is that we are going to read the array backwards in reverse, insert into BST, and then we check the post order. If these 3 things hold, if any one of them, all these are basically valid algorithms to check for the post order of the BST.